Now, ever wondered how your brain, this squishy organ, pulls off feats like recognizing your friend in a crowd or composing a symphony? It's not magic, it's a meticulously orchestrated dance of billions of neurons firing off tiny electrical pulses, spikes. Think of it as nature's ultimate high-speed communication network. So, we've got our biological blueprint. Now, let's pit it against the reigning champ of AI, deep learning. What's the verdict? AI is like a super specialized Swiss Army knife, brilliant at one specific task, but clumsy if you ask it to juggle. The brain. It's more like a jazz band, improvisational, adaptable, learning from every single moment. AI learns in massive offline batches, then goes on autopilot. Your brain? It's constantly tweaking, rewiring itself based on experience. And energy? Oh boy, the difference is night and day. Your brain runs on about 20 watts, less than a dim light bulb. Training an AI model can guzzle megawatts. That's the gap we need to bridge. Alright, so how do we build machines that think more like us? Enter neuromorphic computing. This isn't just software tweaks, it's about building hardware that fundamentally mimics the brain. Think chips like IBM's True North or Intel's Loihi. These aren't your grandpa's processors, they're designed with spiking neurons using asynchronous circuits that only fire when needed, slashing power consumption. We're talking algorithms like spiking neural networks, SNNs, which are explicitly designed to handle information in time, not just static snapshots. And crucially, we're embedding learning rules like STDP directly into the silicon, allowing these systems to learn continuously, adapting their connections on the fly. This is where the real magic happens, hardware and algorithms working in concert. Okay, we have the building blocks. But how do we assemble them into something that feels like a thinking entity? We need architecture. Imagine the brain has a central stage, the global workspace, where all the different departments, vision, hearing, memory, can broadcast their findings. That's the core idea. Then you need an attention mechanism, like a spotlight, focusing on what's important and filtering out the noise. Crucially, you need metacognition, a kind of executive controller that monitors the whole system, evaluates progress, and makes strategic decisions. It's the part that says, I'm stuck here, maybe I should try another approach. This combination aims for continuity, a smooth flow of thought, and ultimately, a self-representation, a sense of I am doing this. So, we've built these complex systems. How do we know if they're actually getting closer to consciousness? We need objective ways to measure it. One promising framework is DIKWP, standing for Data, Information, Knowledge, Wisdom, Purpose. It suggests true intelligence isn't just pattern matching, but transforming data into purposeful action. We'll need a multi-layered evaluation. First, check the structure. Does it have those key brain-like features like re-entry loops and plasticity? Second, observe behavior. Can it perform complex tasks, recover from errors, and explain its own reasoning? Third, dive into cognition. Look at internal metrics like integrated information, PHI, and see if there's evidence of coordinated activity, like gamma waves in the brain. The goal is to create standardized benchmarks, like WAAC's efforts, to track progress objectively and safely. This journey towards truly autonomous, brain-inspired AI is happening now. Organizations like WAAC are setting the stage, coordinating global efforts, defining standards, and pushing ambitious milestones like simulating mammalian brains by 2030. It's a collaborative race, requiring open science, ethical foresight, and incredible technical leaps. The potential is immense, paving the way for a future where humans and AI evolve together, tackling challenges we couldn't even imagine today. Thank you.